It's located at the Brookhaven National Laboratory on Long Island. It's like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around this 2.5-mile circular tunnel in opposite directions, 78,000 times a second, and then collide inside this giant detector, bigger than a 3-story house. When they smash into each other, they generate incredible heat, just like the real infant universe.
We believe the early universe was extremely hot, billions of times hotter than the center of the sun. And what you're doing when you're smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. It's a bit like discovering what cars are made of by watching them smash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
What the scientists at Brookhaven have discovered is that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories on the nature of the early universe. Because it's not a gas, it's a liquid. It was super hot, 100 million times hotter than the surface of the sun. There was so much energy inside the young universe that the particles vibrated so fast that it had no stickiness. There was no friction, and it flowed perfectly.
This liquid is perfect. It has no viscosity. In some sense, it would be the perfect motor oil, except it's 1 trillion degrees hot.
Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second. The Brookhaven scientists have succeeded in recreating conditions that existed over 13 billion years ago. Despite the universe being a perfect liquid, it was in turmoil. It was full of subatomic particles smashing into each other, releasing more and more energy. There was so much energy that unless the particles slowed down, they would never bond and create atoms, the building blocks of matter. And the universe would never create the galaxies and stars, or even us. The universe is now 1 millionth of a second old and has expanded from smaller than the size of an atom to 8 times the size of the solar system. After the incredible turmoil of the first millionth of a second, the universe was now relatively calm. Over the next 3 minutes, the expanding cosmos cooled sufficiently for protons and neutrons to bind together and form the first atomic nuclei, hydrogen and helium. These were not yet proper atoms. They were missing a vital ingredient, the electron. In the hot baby universe, there were plenty of electrons around, but there was still so much heat and energy, the electrons were moving too fast to form bonds. And it would stay that way for over 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees Fahrenheit to a few thousand. As it cooled, the electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment in the story of the universe was Arno Penzias. 1963, 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. But the explanation for their mystery background noise starts not with sound, but with the birth of light. We usually take light for granted, but in the early universe, 13 billion years ago, we would see nothing at all. Light was trapped. The universe was foggy. But as the universe continued to expand and cool, the electrons slowed down. Protons then grabbed these calmer electrons to form complete atoms of first hydrogen and then helium. The universe was suddenly much less crowded with electrons. The fog lifted, and light was no longer trapped. It hurtled out across the universe, creating a blinding burst of light.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift, and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13-billion-year-old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a... That's what we call noise. If you have a good radio set, 0.1% of that is actually the sound of the Big Bang.
And we can also see the moment when the first elements were created. If our television is not tuned to a station, a tiny fraction of the noise is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms.
Over the next millions of years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in is made from more than 100 different kinds of elements. Without them, the universe would remain a very boring place, made up of only gas, a place where complex matter, like planets, cars, and people, could never develop. The universe needed to get hydrogen and helium atoms to fuse. And to do that, it needed to make stars. The universe was now 200 million years old and billions of light years across. Its temperature had dropped so far that it was colder than liquid nitrogen, minus 300